Okay, so on to the third and possibly the most exciting handout ever. So I said that on Blackboard. This is a momentous handout and we have to relish in its awesomeness because it is totally awesome. So this is where we're going to learn about organometallics, which make more carbon-carbon bonds. And you remember how excited I got when we made carbon-carbon bonds with alkynes? Well, I'm going to get doubly excited about this one. Okay, so again, we're going to learn about organometallics, and this is awesome. Okay, organometallic compounds contain covalent bonds between carbon atoms and metal atoms. Okay, carbon and metals. Carbon and metals. And the carbon-metal bond is polarized with the positive charge on the metal and the negative charge on the carbon. Whoa! These compounds are very useful because they have nucleophilic and basic. This is important later, but importantly, we have nucleophilic and basic carbon atoms. All right, so these are what organometallics look like. Organometallics. They are called as such because they have an organo portion, an organic portion, as well as a metallic portion. So, RM. Here's the organic portion. Here's the metallic portion. Okay, and usually M equals magnesium X, magnesium halide, or a lithium. These are the metals that we use. Okay, we don't use any other weird metals. It's usually just magnesium halide or lithium. Okay, so these organometallics look like this. Look like RM. I'll obviously show examples in just a second. But in doing so, the metal has the positive charge. So it's got a partial positive over here. And importantly, the organo portion, the organic portion, has a partial negative. Okay, that's again because metals, right, like to be cations. If we think about sodium chloride, sodium is the cation and chloride is the anion. So if we have like a sodium here, but again, we don't use sodium, we use magnesium or lithium, but still we have a metal here, it likes to be the positive. So when we use them in reactions, they act like R minus M plus. Just like whenever I write NaOH, I write Na plus OH minus. We'll do the same thing here. Just put the R minus, just put the minus on the carbon. Put the minus on the carbon. Or R minus. Oh my gosh. Oh my gosh. So again, these make carbanions. Carbanion nucleophiles. Hooray! Okay, again, the carbon is nucleophilic. This is amazing. Carbon is nucleophilic. So, here's a great example. Here's methyl lithium. Okay, this is how we would draw it. Okay, but how does it act? It's going to act like this. CH3 minus Li plus. Okay, and this is an organolithium. That's what we would call it. We're going to discuss these differences or discuss these different reagents in just a second. Or, again, we can also have MgX. So here is phenyl Grignard. We're going to see these. MgX are Grignards. Okay? These actually are more like, here we go. I know it's expanding the octet. That's why it's just kind of like this. Okay? And MgBr plus. Okay? Again, we'll put quotations around him. Because again, this is how they act. Okay? And this is known as a Grignard. Obviously named after an actual chemist. This one, they didn't get named after the chemist. They just called it organolithium. Whenever we use the magnesium, it's called the Grignard, and the magnesium always has a halide with it, or you can just use the simple lithium, and it's an organolithium. Okay? The two most common classes, as it says there, organometallic reagents, again, the organolithiums or the Grignards, can pretty much be used interchangeably. There you go. These reagents are extremely versatile and can easily add to carbonyl electrophiles, such as aldehydes, ketones, and esters, which are some of our best ways for forming carbon-carbon bonds. Yes. Yes. Okay? So, again, let's remember how excited I got when we did this with alkynes. Okay, so if we had a terminal alkyne like this, right, we deprotonated it with what? What was our favorite base to use for deprotonation of alkynes? It was NaNH2, sodamide. Remember I did that whole story of sodamide, right? This can go and deprotonate, right, because the alkynes are relatively acidic, right, which gives us CH3C. Remember our carbanion? Yay! Carbanion. Again, this is an awesome nucleophile. So then when we threw in our electrophile, which again you guys should all have seen and remember from your homework, okay, we could go in and attack that carbonyl. Remember, it was very electrophilic at the carbon, right? And then after our acidic workup, I'm not going to draw it, but after the acidic workup, okay, we would get a racemic alcohol. So we get OH, C, CH3, okay? And this alcohol, the enantiomer, C123, CCH3. Okay, we get racemic, and of course it would be an alcohol. Remember this? Why do we get racemic? I know I put this in the homework. I don't think we explicitly went over it in class, but hopefully you figured it out in the homework in the sense of this carbon. What is its hybridization? This one right here, the hybridization of the carbonyl carbon. It's sp2, which means its geometry is trigonal planar. It's flat. So again, this nucleophile can attack from the front and push the alcohol back, or it can attack from the back and push that alcohol forward. Either or, it's flat. So it can do either side equally, which is why we get a racemic mixture of these enantiomeric alcohols. Okay? Well, organometallics are the same. Again, remember how excited I got? Well, again, I'm trying to contain myself because it is amazing. But organometallics are the same. And it's just great because you can make pretty much any carbon a nucleophile. Okay? So if we have CH3 MGBR, okay, I will draw the mechanism in on the next page, but right now we're just going to go through examples. We throw in a carbonyl, and again, we do need our acidic workup. Okay, just like up here, here's our carbanion nucleophile. Carbanion nucleophile. Okay, and in the end, we are again going to get a racemic mixture of alcohols where the methyl has added. CH3, oops, this one's not racemic because we need more carbons. Here we go. There we go. Now it's enantiomeric. Now it's chiral. There. Now it's chiral. Plus, here we go. We can attack from the front, pushing that alcohol back. Okay. Awesome. And of course, it is racemic, and importantly, it is an alcohol. Okay, so just like with the alkynes, when we attack the carbonyls, we got alcohols. It's the same thing with our organometallics. Okay, here again, the carbon is the nucleophile. It will attack. It's going to get protonated. Again, I'll draw this mechanism on the next page, and we get our alcohols. And why are they racemic? Again, because this carbon is sp2 hybridized. It is flat. So we can attack the front or we can attack the back equally. Okay, here's another example of an organolithium doing the same thing. Look at this, really cool carbon nucleophile. Let's add to an aldehyde electrophile. This time we will get, again, a racemic mixture. I'm going to draw it a little bit differently though. I'm just going to kind of attack from underneath and put that H, because this is how we normally draw things. We put our longest carbon chain in the plane of the paper. But still, it's done the same thing. Okay, it's attacked from the back to push that alcohol forward, or it's attacked from the front to push that alcohol back. I've just rotated it a bit to put the H as our other group. So again, this is going to be racemic, and again, we get an alcohol. Hooray! But importantly too, right? Here was a carbon, here's a carbon, bond. Carbon, carbon, bond. Yay! Okay. Organometallics. Plus a carbonyl. When we mix these guys together, we get an alcohol. With importantly, a new C-C bond. Oh my gosh, it's momentous. Okay, and we will denote this with the new color again, saying how awesome it is. Hopefully you'll want to use these all the time. I'm sure you will. Okay, they do have limitations, but still, for now, let's just be excited that we can make pretty much any carbon a nucleophile. Yay! Okay, so again, there were two main classes, right? The Grignard reagents and the organolithium. So let's look at these and kind of look at their similarities and look at their differences. In the end, they're just very, very similar. So Grignard reagents result from the reaction of an alkyl halide with magnesium metal. That's all you do. You throw in your alkyl halide, magnesium, and you get a Grignard. It's that simple, okay? These can be made from primary, secondary, and tertiary alkyl halides, as well as vinyl and aryl halides. Here is our vinyl halide, okay? Sorry, vinyl lithium. So if we just imagine lithium being an X, there's our vinyl halide. And aryl one just has an aromatic group, has a benzene, okay? The most common solvent for these reactions is diethyl ether, which is needed to stabilize the Grignard reagents. There you go. And this is what they look like. So here is methyl iodide just normally, before it has reacted with the magnesium. You can see here that on this side it's blue. And for these electron density maps, blue means we are electron deficient. Okay, and we can see though that the halide, the I, is very red. Okay, so the red means electron rich. And this makes sense, right? Because electron rich. The halide is more electronegative, so it's pulling electron density like this. And so we can see that in our electron density map. That's what's going on here. Okay, we can see that all the electron density is around the iodide. However, as soon as we throw in magnesium and we make CH3 MgI, so here's our methyl Grignard, you can see, look at this. It's not quite red, but it is more electron rich. It's definitely not blue. It's definitely not blue. Okay, so here we can see that the CH3 is electron rich, and therefore it is a nucleophile. Okay, which is awesome. Yes, we still have electron density around the iodide, but we can see that it's just by binding to this metal, again, which doesn't want any electrons at all, it gives them all to the carbon. Okay, so here we can see we are now made it nucleophilic, and that's amazing. So how do we make these reagents? Again, we just throw in magnesium. Let's go over the mechanism for how they're actually made. And then I think we'll have to call it a day. Ooh. All right, so how do we make our Grignard? Make sure I'm on the page. Make Grignard. Okay, so again, we need our alkyl halide, and we just throw in magnesium. Yes, we have ether as our solvent. Ether. But he doesn't do anything. He just sits there and stabilizes everything. And in the end, we get our Grignard, which looks like this. RMGX. Okay? So this mech, it's kind of like our sodium in liquid ammonia mechanism. It's going to have both half arrows and full arrows. Okay, so magnesium, it's got 2 electrons. 2 valence electrons, that's why it likes to make a 2+ cation. But regardless, we also have our halide, and what happens is that one of these electrons will go and attack the carbon. But we can't expand carbon's octet, something has to happen. We lose 2 electrons. Okay, so we move 1 electron here, but we can't, expand carbon's octet, and so we move 2 electrons onto the halide. And the halide leaves to give us R dot plus X minus, okay? And since we lost an electron from magnesium, it also coordinates to the halide, just coordinates because it's got a plus charge, but it still has its one valence electron left over. And so we have two dots in solution, they come together. They find one another. Okay? And we make our MgX. Okay, so it's really just this is an ionic bond taking place here. Just forms, we don't need to show it. It's just an ionic bond. The coordination between the X minus and the metal plus. Okay? So, example of course, you just start with your halide. Again, really can be pretty much any halide. All you do is throw in magnesium. Yes, you do need some ether. It's okay if you forget that. And all that happens is that magnesium just inserts itself between the carbon and the halide. Nice. And then as soon as we throw in an electrophile, I don't know, let's use this aromatic electrophile. Okay, and yes, we do have our acidic workup, which again, I usually leave off. I usually still assume it. Okay, so we'll just write that. Assumed. Regardless, then we get our racemic mixture of alcohols as long as we make a chiral compound. Okay, so here we're going to attack from the back, and here we're going to attack from the front. Nice. Racemic. Okay. We can also just kind of write this as a two-stepper, but one pot. Okay, we can isolate this guy, or we can just kind of do it all in one pot. This is normally how it's kind of written. Just throw in our magnesium, and then an hour later, we throw in our electrophile. So here, after we swim with our magnesium, right, we're going to make our Grignard. Again, just insert that metal in between the carbon and the halide. Okay, so this is the product of I. And then after we've made our Grignard, we just throw in our electrophile and we get our alcohol. OH plus OH, and it's racemic. Okay, so again, we just make these by throwing in magnesium, but you do need to start with an alkyl halide. Again, you need to focus on what you need to start with and what you get out. Okay, so again, to make a Grignard, you do need the alkyl halide. So if we don't have an alkyl halide, let's say we had just an alkane, how would we make an alkyl halide from an alkane? Maybe free radical halogenation. Okay, regardless, we need our alkyl halide, then we just throw in magnesium. That's how we make our Grignard. And then we are nucleophilic at the carbon. Yay! And we'll show that mechanism again soon. Okay, I think that's all the time we have for right now. We will pick up from here with organolithium reagents on Monday.